All right, we are live on YouTube now. So today's topic would be on functions and relations. Again, we're going to do a bunch of problems. And before I do that, there's a few announcements. The first one is quiz number 2 is mostly graded, but we'll release the grades sometime between tonight and tomorrow morning. The homework number 4 will be out this Friday, and a reminder that homework 3 is due this Friday at midnight. And our third quiz is going to come up in roughly a little bit less than 2 weeks, or actually 2 weeks, exactly, October 20th. And again, it's going to be a 1 hour window between 7:30 until 4. And it's going to be on the topic of sets and Boolean algebra. And it's going to cover our lectures 8, 9, and 10. Oh, are you not seeing my, you're seeing my slides changing, right? Okay, cool. All right, next one, which is a fairly important announcement, is regarding quiz number 2. And this is also announced through Canvas, that we did find a few cases of instances of cheating. And we decided we're going to give a one-time scenario where if you let Professor Zvan know about it by the midnight today, you will just get a 0 for this quiz and we'll just move on. But if you do not, then we will proceed with a departmental procedure, which include failing the course, and it will go on your record. So it's just a quick announcement. And if you want to read details, this is also part of Canvas. Okay. All right, any questions? Okay, if there's no questions, let's just get to the practice problems. We're going to do a quick review of what we learned in the previous chapter, which is what you have been tested on quiz number 2, is element-wise proof. It's proof and together with sets relations. Okay, so you have roughly 1 minute to think about how you would prove this problem, and then we'll go over the problem together. Okay, to begin, I'm going to simplify the problem by using some notations. Okay, so this is going to be my proof sketch. And to give you a hint, we're going to prove using set membership. And then, of course, the definition of union and the definition of subset. So to simplify, I'm going to define the first set A to be for all real number that is smaller. Okay, that was a timer that is smaller than -3. The set B is all the element that is bigger than 3. And of course, set Z is all the element whose square is bigger than 9. Okay, so the problem is asking us to show that A union B is a subset of C. Okay, do I have a volunteer how to solve this problem? You can type or raise your hand.
Okay, in the chat, we've got square X and Y.
Square X and Y. Can I get a little bit more detail? Well, it's close, but there is a little bit difference. If you look at it, if I square it, right, I need to prove that somehow the square is bigger than 9. So you are roughly on the right direction, but we need some details. Okay, so let's do this together. So what do we want to show? When I want to show A union B is a subset of C, then if we let an element A that is belongs to A union B, we want to also show A belongs to C. This is by definition of subsets, okay? But of course, if A belongs to A union B, this means A is in A or A is in B, okay? So the first thing comes to my mind is I'm going to prove by case. The first case is A is in A, the second case is A is in B. So case 1, A is in A, and case 2, A is in B, okay? So when is in A, this means that by definition of the set A is smaller than -3, okay? Now if I add 3 to both sides, we have A plus 3 is smaller than 0. And then if I subtract -3 on both sides, that means A minus 3 is smaller than -3, which is smaller than 0. Okay, so both of those are algebraic manipulations. So now we have both A plus 3 and A minus 3 be negative. Now, if you have two negative integers multiplying together, you get positive. So you have A plus 3 times A minus 3 is equal to A squared minus 9 is bigger than 0. So what does this mean? This means A squared is bigger than 9. That means A is part of C. So what I have done here in this first case, these are a few key points. I use the formula A plus B, A minus B is equal to A squared minus B squared. That's the first piece I used. The second piece I used is if you have A smaller than B, A smaller than 0, B smaller than 0, if I multiply them, they are bigger than 0. So the multiplication of two negative negative real numbers give me positive real numbers. Okay, so that is the case A. Let me add a page for case B. The second case. In this case, A is part of, A is part of B. So what does that mean? That means by definition, A is bigger than 3. So now what I can do is I can subtract 3 from both sides. So A minus 3 is bigger than 0. I can also add 3 on both sides. So I have A plus 3 is bigger than 3, which is bigger than 0. So again, I can multiply two positive real number together, which is also positive. So A plus 3 times A minus 3 is bigger than 0, which means A squared minus 9 is bigger than 0, A squared bigger than 0. So A is part of C as well. So if you go back to both cases, I have showed in case 1 that if A is in capital A, it's part of C. In case B, I just showed if A is in B, it's also in C. So now you have shown the final result, which is A union B is a subset of C. Okay? So if you are going to write this in detail, this is a detailed proof. But I have just went over the high level. Really, at the key point of the proof is relying on A squared minus 9 is bigger than 0. So one of the students who said, taking the square, you are in the right direction, but the most important part is to show a square minus 9 using the formula a plus b times a minus b is equal to a squared minus b squared and some algebra manipulations. That is a key point of this proof. So it's using this as well as negative integer, multiplying two negative integer yield a positive number, multiplying two positive number yield a positive number. Okay, any questions? All right, so let's move on to the next one. So this new chapter we are learning are related to functions and relations. So
Sorry, there is a question real quick.
yes, go ahead.
Why can we multiply the two numbers?
Why can we or why cannot?
Why can we?
Why can we? Okay, so here is the initial thing, right? If you look at the way to guide you is to look at what's the property associated with the element in the set C. I have something in the form of z square, and on the right hand side is a z square minus on the right hand side is 9. So if I use this space here, what we have is if you look at the element in C, element in C is z square bigger than 9. So if I were going to motivate or sort of give myself some guidance, one way to look at it is to do some algebraic manipulations. It's looking at z squared minus 9 is equal to z, is bigger than 0. And when you see this, what would happen is there is a formula, as I mentioned before, is a formula a plus b times a minus b is equal to a squared minus b squared. This is a formula that comes to mind. So when you see this, you can factor it into those two terms, which looks like elements from set A and set B. And that's what help you guide towards. Is this answer your question? There is, okay, so if I understand your question, the other aspect of this is when I have two things multiplying together, I want to show them that their multiplication is bigger than 0. There's usually two scenarios. One is both of them. So actually, let me not use this one, but let's just use this as a thing. So if a squared b squared is bigger than 0, that means a plus b times a minus b bigger than 0. There's two cases. Case number 1 is both a plus b a minus 1 is bigger than 0. 2 is both of them is smaller than 0. If only one of them is bigger than 0, the other one is smaller than 0, you know their multiplication is less than 0. Okay, so that's what you rely on. Any more questions? Okay, if there's no more questions, let's move on. All right, so now you have 1 minute to solve this problem on functions. You have a set with 3 elements, A, B, and C. Define the function from P of X to P of X. So P of X, this means it's a power set of X. With a rule that when I take an element from the domain of the function, it maps to the complement of it. So for example, if I take a subset of X, which is, let's say it's element A, then C of A of this set is equal to X minus the set. So what is X? X is ABC. So this is everything in X, but not including element A. So this is equal to B and C. So this is set difference right here. And this is a power set. And what the problem is asking is to generate a two-set arrow diagram of this function. So this is a visualization of what is in the domain and what is in the range of this function and how those elements map into one another. To begin, we can start drawing those two sets of sets, right? Which are both power set of X. All right. Okay, do I have a volunteer? What is in the power set of X? Okay, so Sevin, go ahead.
So in the power set, would it include the empty set?
Yes, power set is a very important part. Power set include the empty set. Okay, go ahead. What is in the power set?
So there's the empty set and A with brackets around it, and B, C, A, B, A, C, and B, C. Oh, and then there's also A, B, C, I guess.
Perfect. Right, remember the size of the power set is 2 to the number of n, where n is the size of the set, right? So as what you stated here, part of the empty set, or part of the power set is the empty set, the singletons, and then every 2 elements, and every 3 elements. Okay? But I need to use a 2-set arrow diagram to show the function. So the function is mapping the domain, which is left, to the codomain or the range of this function. So what is a mapping? If I fit in C of empty set, what is the output?
Isn't it all of the sets except the empty set?
Yeah, which is itself, right? So what does this mean is that if I take the empty set, it's going to map through an arrow to its output of the function, which is the entire set. Okay. What about if my input is A, the set A? What is the output of this function? I kind of hinted right here.
In the chat, David said BC.
Yep. Okay. Let's see what the next one. B goes to.
Okay, Kevin said AC.
Great. And C goes to.
AB.
Okay. All right, great. So as you see a pattern, what I'm doing is I'm matching an element in the domain to an element in the codomain. And in this case, the relation between an element in the domain and its image in the codomain is a set difference. So if I keep going, AB is going to map to C, AC is going to map to B, BC is mapped to A, and ABC is going to map to empty set. So the important part of this problem is remember empty set is always an element from the power set. And the second thing is remember a set itself, sorry, it's actually I should use this. A set itself is an element from the power set. Okay, any questions?
There are a couple in the chat. So Ashton asked, is this an inverse function?
Is this an inverse function? What do you think? First of all, if you think about an inverse, in fact, we're going to come up with a question to prove something has an inverse. To show a function that is inverse, it has to be 1 to 1 and onto. And this function is 1 to 1 and onto, therefore it is inverse. It's an inverse function. Yes. Keep going. Any other questions?
Yes. What is set A?
Oh, so letter A is a variable. So it is a rule of taking an element in the domain then map into something in the codomain. So A is a variable. So you replace A by a set that is having one element or the empty set, or you can replace it by any element in the power set itself. So this is a variable. representing any set that is a member of the power set. Okay. If there's no more question, let's move on. This is exactly so. One of you asked a very nice question to ask whether a function is invertible, and we now have a proof. So you have 1 minute to think about the proof to show that my function g takes real number to real number. And I want to show with a rule of g of x is equal to 5x minus 7. Again, x here is a variable that represents an element in the set R, which is a real number. We want to prove g is invertible by proving it's 1-to-1 and onto. Okay, while you think about it, I'm going to quickly review.
There is one question,
Yes.
last minute question from the last problem.
Okay.
Can A have any value that isn't in X?
It's A takes a value of an element in P of X. So remember, P of X is a power set of the set X. So its element, so P of X is a set of sets. P of X is a set of sets. It contains set with 1 element or with 0 element, set with 2 elements, and so on. And set with 3 elements. That's a power set. So A replaces every single element in the power set, which represent the element in the domain of this function. So what is the domain? Domain of the function is the power set of X. Codomain is also the power set of X. So A represents an element in the domain. Okay, so it's going to represent all of those 8 different sets as a variable. Okay, all right, so before we go to the proof of this, let me quickly review the idea of a 1-to-1 function. And also the idea of an onto function. So 1-to-1 function, by definition, it's if my function f goes from x to y, x is a domain, y is a codomain. F is 1-to-1 if for all element AB that is in the domain, if FA is equal to FB implies A equal to B. Okay, so that is the definition. So if I have 2 elements from the domain that map into the same function value, then those 2 elements has to be equal. Of course, equivalently, what does this statement mean? It means for all AB is in the domain, I can take the contrapositive statement. That means if A is not equal to B, implies FA is not equal to FB. So what does this mean? This means that if I have distinct elements in the domain, they map to distinct elements in the codomain. So the typical pictures of it, I'm going to draw a bunch of pictures. Again, using the arrow diagram we just saw. And you can tell me if this is 1-to-1 or not. So this is element 1, 2, 3. This is element A, B, C, D. Yes, go ahead.
So Brendan asked, what if A is -2 and B is 2 and f of x is, I think that, I'm not, there's like a caret sign. I don't know if that was intentional, but oh, f of x is squared. Okay.
Fx is x squared. What is the function looks like? I'm confused. What if A is -2 and B is 2?
F of x is x squared.
So what is the question?
So let's see. So if a is -2 and b is 2 and f of x equals x squared.
What is the question? This is just a...
So wouldn't, let's see, f of a would be 4.
I see. Okay, so you're giving me a specific thing. Let's say f is... So is your domain just those two numbers, or your domain is all real numbers? So let's assume your domain is all real number. You're just giving me some examples, right? So you're giving me an example like this, okay? And then then there's many other numbers in here, but -2 and 2 is just two example in the domain. And it's through this, they both map to the element 4 in the codomain, okay? So is this function one-to-one? Remember it says, if I have two distinct elements, they have to map to distinct function values. So the answer is this is not one-to-one. Because when I have 2 not equal to -2, but f2 is equal to f minus 2. So this condition that is highlighted in yellow is not satisfied. Okay. All right, let's go through the example I was drawing. So is this function I just drew one-to-one?
There's a couple answers in the chat saying yes.
Great. This is yes, this is one-to-one because two distinct elements map to distinct elements in the codomain. Distinct element in the domain map to distinct element in the codomain. Let me draw another one. Is this one-to-one?
All right, from the chat, yes.
Again, by definition. The third one, which is very similar to the one that we just asked. Is this one-to-one?
Lots of no's.
Good, because the important part is I have elements 3 and 4. They are different, but they all map to C. Okay. And now the last one. Is this one-to-one?
All right, no as well.
Yeah, it's actually similar. It's in the same scenarios. 3 and 4 both map to the same element. All right, so that's about one-to-one. One-to-one function, remember, is distinct element in the domain mapped to distinct element in the range or codomain. Here, a function is onto. So, by the way, in one-to-one function is also called injective function. And onto function is also called surjective function. So for a function to be onto, so f of x to y is onto if for all y in the codomain exist x in the domain such that f of x is equal to y. So that means for every element in the codomain, I have something that map to it. Okay. So
Jacob,
let's do a
the
quick
chat,
example.
there-
Yes, sorry, go ahead.
could there be a case where an element in the domain is not mapped?
Ha, then that is not a function. So you're talking about this situation. Okay. So there means that there's something in the domain that is not mapped. This is not a function. Okay. All right, but let's look at the onto function. An example of an onto function is one such that for every single element in the codomain, something is mapped to it. So this is an onto function because for every element in my codomain, something in the domain that maps to it. However, is the one that I have enclosed by the purple line, is this an onto function?
No.
No, because the element highlighted in pink, the element D has nothing in the domain that map to it. Okay. All right, let's go back to the proof. We want to prove this function is both one-to-one and onto. Okay. So do I have a volunteer? How do we approach this problem? Of course, you want to first show G is one-to-one, and also you want to show G is onto. So if G is one-to-one by definition, of one-to-one, we want to show that if A is not equal to B, if, let me use the original definition, show that if G of X is equal to G of Y, we show that X is equal to Y. Okay. Do I have a volunteer? This proof is roughly 2 lines, but if you expand it, it's 4 lines. Okay, go ahead, Sabine.
So for the first one, we can like let x1 and x2 be in Z, the set of integers.
Oh, no, set of real numbers. The domain's real.
Or real
Yeah.
numbers.
Okay.
And plug those in the 5x minus 7, or plug in G of X.
So you're assuming G of X1 equal to G of X2, right?
Yeah.
Because you are using the hypothesis as this definition right here.
Yeah.
Okay. And then so you plug it in. So you have 5x1 minus 7 is equal to 5x2 minus 7. And then what?
And then you add 7 on both sides and divide by 5. And since x1 equals x2, we complete case 1.
Of course, what I wrote here is sketch, right? But what you do is you assume you have 2 elements, x1, x2, and such that G of x1 equal to G of x2, and you show that x1 equal to x2. Then you show G is one-to-one. Great, thank you. All right, now we want to show G is onto. Remember, by definition of onto, you want to say for all element in the codomain, there exists an element in the domain such that G of X is equal to Y. So for any element in the codomain, there's an element in the domain that map to it. So this is what we want to show. Okay, do I have a volunteer?
There is a question in the chat from Brendan.
Yes.
Are there any cases where x1 equals 2, but g of x1 does not equal g of x2? So far, all the examples I found all show that they're equal.
Yes, yes. I mean, in this particular problem, you want to show it's one-to-one. That means this is actually for any xy that is in R. So you can't, in this particular case, you can't prove it by example because you have R, which is an infinite set. So you actually have to prove by the definition of one-to-one function to show that for any pair where if G of X is equal to G of Y, then we want to show X equal to Y. You can use examples to convince yourself the statement is true, but you need to use algebra to prove this. Okay. All right. Do we have a volunteer to show how G is onto? We just want to be able to solve for any real number in the codomain. There is a number in the domain that map to it, right? So what we have is we can take a variable z, which is equal to y plus 7 over 5. And we show that g of z is equal to 5 times z, which is y plus 7 over 5 minus 7. By algebra, this is equal to y. So that means for all y, I have a corresponding z in the domain that map to it. However, we have to be a little bit careful. How do we know that z, which is y plus 7 over 5, is part of the domain, which is real? So you want to use by closure property. So since y is real and z is real by closure property of real number. Okay, so this is just a sketch. The next page, what I showed is how you write it in more cleaner way. Is if I assume a y that is in my codomain, I can find a x such that find a number z such that g of z is equal to y. If this is indeed the case, then my function g is onto. Okay, but the important part of this proof is we want to show the number z is a real number. And that is because of the closure property of real number under addition, multiplication, division, and subtraction. Okay, any questions? If there's no questions, we're going to move on to a few easy questions.
I have a question,
relation.
sorry.
Yes, go ahead.
I can't type fast enough.
Okay.
Just in the Prask problem, do you get the z equals the quantity of y plus 7 divided by 5? You get that by solving for, I mean, I guess solving for x?
Yep, exactly.
With the formula?
Yeah, that's exactly what we did, in fact, because you are, think about there's a function f that maps from domain to the codomain, and I have something that map to it. So I take an element y that is in my capital Y here is R, and my domain is also R. So my function map from R to R. So I have an element Y in R. I want to be able to find an element in the domain that map to it. So in this case, I'm using the variable Z. So how do I do that? I have Y equal to 5Z minus 7, then Z is equal to Y plus 7 over 5. That's how I find it. But the most important part is I need to show Z, by doing this, is part of the domain. Does that make sense? So you need to be able to use the closure property here. Okay. All right. So this one should only take you roughly 20 seconds. You have a relation on a set, and then relation is less sign. So a pair of element in A is form a relation when x is less than y. So whenever we describe a relation on a set, in fact, to be more precise, my relation R is essentially a subset of A cross A. So it consists of a set of ordered pairs based on the relation less than, okay? So can someone tell me what are the pairs that is ordered pairs that is part of this relation? Do I have a volunteer?
David said 2 and 3, 2 and 4.
Mm-hmm. Missing one.
3 and 4.
3 and 4. Right? So those are all possible pairs of element in A cross A, such that the first element is smaller than the second element. So this is describing the relation on A cross A using the symbol less than. Well, the next question, so of course I type it here. Next question, what is the inverse of this relation? And describe it in words, right? Remember the previous relation is 2, 3, 2, 4, 3, 4, parentheses. What is the inverse relation? Do I have a volunteer?
Go ahead, Savine.
It would be 3, 2, 4, 2, and 4, 3.
Yeah, great. So we want to describe it in words. What do the words mean? What is a new relation that is describing R inverse?
In the chat, Jackson said X is greater than Y.
Great.
And Mohammed said X and Y are swapped.
What is the second one?
X and Y are swapped.
Yes, but it's better to describe it this way. Okay, it's swapped. It's based on the previous context. But if we want to describe it by English, we will say X is greater than Y. Right? It's swapped with respect to the relation X is less than Y. Okay, all right, so this is all easy. Now let's look at next one. Now I have, again, R is a relation on the set of non-negative integer. So R is now a subset of, again, sorry, X cross X, right? So it's not another ordered pair. It's defined by the equation X squared plus Y squared is 25. So we want to write R as a set of ordered pair. Any volunteer?
Jackson said 3, 4 and 4, 3.
Great, but almost there. The hint is to find non-negative integer solution. There's one more pair of solution.
Brendan said 5, 0 and 0, 5.
Exactly. So that's what it is. The relation is determined by X squared plus Y squared is 25 and X, Y are non-negative. So there's two pairs of potential solution and then they form ordered pair. So you need to include both 3, 4, 4, 3, 5, 0 and 0, 5. Right? Okay, moving pretty fast. Next one is, again, going back to the arrow diagram. Sometimes we also call it directed graph. We want to represent a relation on a set. The set has, in this case, 4 elements. So element 1, element 2, element 3, and element 4. And now what I would like you to do is to use the arrow diagram to show the relation R on the set X. Okay, you have 15 seconds to do this. Okay, do I have a volunteer? How does my arrow diagram looks like?
In the chat, Brendan said 1's arrow loops to itself. 2's arrow loops to itself.
So that's 1, 1, 2, 2, okay? What else?
2 points to 3. 3 points to 2. And 4 points to 2.
Exactly. That is my arrow diagram. That shows a relation among the elements in X. Okay. All right, this one is going to take a while, and I want you to spend 1 minute thinking, and I will give you a sketch of this curve. So if you have relations, you can define what's called a composition. So what I want you to prove is prove the composition of relations satisfy the associative law. So you have A, B, C, D to be sets. R is a relation from A to B. S is a relation from B to C. T is a relation from C to D. And you want to prove R composed with S composed with T is equal to R composed with S and T in the second order. So I can have commutative relations, associative relationship between those relations specifically, okay? And to give you a hint, if I want to prove those two, remember when I compose relation, I still end up getting pairs of elements in the relation. So the left-hand side, you can think about it as a set, and the right-hand side, you can think about it also as a set, okay? So do I have a volunteer to tell me what is a high-level picture to how to prove this? There's two parts of this proof. Remember, if I want to show two sets A is equal to B, I need to show A is a subset of B and B is a subset of A. So what you want to do is, in this case, you want to show the left-hand side is a subset of the right-hand side. I'm treating all those composition of relation as a set of ordered pairs. So they are set relations. The second part is I want to show the right-hand side is a subset of the left-hand side. So that is a high-level picture. Now I'm going to go over part one. Do I have any volunteer? I think this is a little bit tricky problem, but let's do this. I'm going to add one more slide, just review the relation of composition. So if I have AB belongs to composition of the relation R and S are relations. This means there exists an element C such that A and C belongs to relation R, and C and B belongs to relation S. If I think about an arrow diagram, this is what I have. I have an element A and C, where A and C has a relation in R, C and B has a relation in S. Then the relation between A and B is a composition of these two relations. Okay, so that's what it is. Let me just draw the arrow. So that is a property we're going to use quite a bit. Okay, so let's do this. What I start with is I start with an element on the left-hand side. So I will start with an element. Now, if I have an element in a relation, it's a pair. So I have an element AD that belongs to the left-hand side. Now I'm just going to use the definition of relation composition. So that means, this means there exists C such that A of C belongs to the first part of this relation, and C of D belongs to the second part of the relation. This is just using definition of relation composition. That's the first thing. Now, because A of C belongs to R composed of S. I'm going to use the definition of a composition one more time. That means there exists B such that A of B is part of the first part of the relation. And B of C is the second part of the relation. This is again applying the definition of composition one more time. So now what I have, because we have BC in S and CD in T, this implies B of D is part of the composition. This is again using the definition of composition, right? I have BC in S, CD in T. If I compose them, then I have BD is in the composition of S composed with T. And because A of D is in R and B of D is in, sorry, A of B is in R. Sorry, that's a typo. And B of D is in S composed R. Then we have AD is in R composed with the result of S composed T. So I start with, let me use orange. I start with, suppose A and D is part of the left-hand side, and arrive at it's also part of the right-hand side, which means the left-hand side is a subset of the right-hand side, okay? And the second part is proved similarly, okay? So that's it. This is probably the hardest part of today's lecture, is to prove the composition of relations satisfy the associative law. So I would encourage you to try to do the second part using the same philosophy as what I just did, okay? So that's it for today. And do I have any additional questions?